This lecture is about scientific notation. So, to start out with, what is scientific notation? Well, scientific notation is just a particular format that we use to write really big or really small numbers. We essentially use what we know about exponents to take numbers that have a lot of zeros in them and rewrite them in a shorter way. So, for example, what are some things we might want to write in scientific notation? Well, for example, the speed of light. That's a pretty big number. Light travels pretty quickly. It's approximately this many meters per second. Right? 300 million meters per second approximately. That's a lot of zeros to write. There's a faster way to write that actually. Using scientific notation, it turns out, we can write this much more quickly, like this. We'll see how to do that in a moment. Much faster to write. Here's another example. The radius of a proton. If you've had some physics before, you've seen a proton as one of the particles in an atom. So really, really tiny. So the radius will be really, really small. And in fact, it's about this many millimeters. Really tiny. That's 11 zeros there, by the way. And so, in fact, this can also be written with scientific notation. It would look like this. Notice much shorter. So, what do we want to be able to do with scientific notation? Why are we interested in it? Well, we can see we're interested in scientific notation because it lets us write really big or really small numbers much more quickly. Anything that has a lot of zeros in it, we can write more quickly using scientific notation. And in particular, what do we want to be able to do with scientific notation? Well, the main two things we want to be able to do is we want to be able to take standard numbers in standard notation and write them in scientific notation. And vice versa. We want to be able to take numbers in scientific notation and write them in standard notation. And what is standard notation? Standard notation is just the normal way we have of writing numbers. Right? 300 million up here is in standard notation. Right? This really long decimal here is in standard notation. We also sometimes want to be able to take numbers in scientific notation and to multiply them or divide them, but actually we already know how to do that. That's just the same thing that we've already done with exponents in general. Because scientific notation is just things written in scientific notation are just expressions that are written as a product of a number and 10 raised to some exponent power. So because we know how to simplify exponent expressions, we know how to multiply, divide, and simplify scientific notation expressions already. Okay, so let's actually look more carefully at what scientific notation is. So we've seen, the two examples we've seen so far involve writing a number times 10 to some exponent power. And in fact, powers of 10 are going to be really important to scientific notation. You'll notice that our entire number system, the way that we write numbers generally, uses what's called a base 10 number system. This means that every place value is a power of 10. The ones place, the tens place, the hundreds place, the thousands place. Same thing for the decimal part. The tenths place, the hundredths place, the thousandths place. Each of these places is actually a power of 10. And so because our number system is based on powers of 10, it means that powers of 10 then are going to have a special pattern when we write them out. So let's take a look at some examples. What are the patterns? Notice in this class we're going to stress patterns a lot. So let's start with this. Let's start with the simple ones. We know 10 to the 1 is just 10 by definition, right? We know that 10 squared is 100. 10 cubed, we just take 10 squared and multiply it by another 10, so that's 1,000. 10 to the 4th power, that's going to be 1,000 times another 10. That's going to be 10,000. You'll notice if we look at this, there's a pattern. The exponent and the number of zeros are the same. So when the exponent is 1, there's 1 0. When the exponent is 2, there are 2 zeros. When the exponent is 3, there's 3 zeros. This makes sense because 10 to the 1 is 10, which has 1 0. And then every time we raise the exponent power by 1 more, we're multiplying by 1 more 10. And when we multiply by a 10, we end up essentially just adding a 0. So we'll notice that the pattern as we go on is going to be that if we have 10 to the nth power, we're going to end up with a 1 followed by n many zeros as we go up. In other words, in these examples, the number 1 is in the 10 to the nth place. Right, so here the 1 is in the tens place, here the 1 is in the hundredths place, here the 1 is in the thousandths place, you see that, and so forth. Okay, now we know from the previous lecture that 10 to the 0 power is just 1. That follows our pattern. You can see it has 0 ones next to it. What about 10 to the negative 1? Well, 10 to the negative 1 we know is the same thing as 1 over 10 to the 1, which is the same thing as 1 over 10, which is 0.1, or 1/10, right? Ten to the negative 2 is similarly 1 over 10 squared, which is 1 over 100, which is 0.01, or 1/100. 10 to the negative 3, similarly, 1 over 10 cubed equals 1 over 1,000, which is 0.001, or 1/1000. So we kind of see a pattern here too. We notice that if we keep going, 10 to the negative n, and here we're assuming that n is a positive integer. You'll notice 10 to the negative n is going to be equal to something that has a 1 with n minus 1 many zeros between the 1 and the decimal place. Now notice the difference. There aren't n many zeros. Notice 10 to the negative 1, there's no 0 after the decimal point. 10 to the negative 2, there's only 1 0 after the decimal point. 10 to the negative 3, there are only 2 zeros after the decimal point. You can see that this is going to be the case because the tenths place is the first place after the decimal point, and the hundredths place is the second place after the decimal point. This is different from the instances of positive exponents because the first place to the left of the decimal point is the ones place. It's only the second place that is the tens place. Notice, again, in this example, though, it does have the same pattern in the sense that the 1, the number 1, is in the 1 over 10 to the nths place. So if we look at this pattern, we notice that what happens is that multiplying by powers of 10 essentially give us a number that has a 1 in a particular place value. This is really useful because if you think about it, what it can actually do is multiplying times 10 to the 4th, for example, will end up having us add 4 zeros onto the end of whatever we're multiplying by. Multiplying in contrast by 10 to the negative 3 will tend to move the decimal place over, make it smaller by 3 decimal places. So let's take a look at examples to see if we can see how this actually works. But we notice that there's this pattern in the tens. Because we live in a base 10 number system, because that's the number system we've invented and that we use, powers of 10 have a special pattern. You can see that really powers of 10 really just involve moving the decimal place back and forth. When the power is positive, we end up with a big number with lots of zeros. And when the power is negative, we end up with a small number with lots of zeros. Something really close that gets closer and closer to 0. So the idea behind scientific notation is this. Any number, and in particular we tend to be interested in really big numbers or really small numbers. In particular, what we're interested in can be written as a product of some number between 1 and 10 and a power of 10. Why is that? Well, that number between 1 and 10 can include anything, any digits in the number that are not 0. And the power of 10 is what can be used to tell us how many zeros come before or after this particular non-zero digits. So let's look at an example. How would we do that with the examples we had before? So the speed of light. The speed of light is 300 million meters per second. So how would we rewrite this in scientific notation? Well, we want to write it as a product of a number between 1 and 10 and a power of 10. Well, notice we have all these nice zeros. Those can be rewritten in a sense as a power of 10. We can rewrite this as 3 times and then 100 million. We can rewrite this as a number between 1 and 10 and this part here, which is a power of 10. We're essentially taking numbers and breaking them into the parts that have zeros and the parts that are non-zero digits. So, but we can keep going from here. How can we keep going from here? Well, we know that 100 million is what power of 10? That's 10 to some power. We know it's going to be a positive power because it's a big number. Well, we can essentially count up the number of zeros. 1, 2, 3, 4, 5, 6, 7, 8. 3 times 10 to the 8th power. So here we have the speed of light written in scientific notation. Let's try this again with the radius of a proton. So if we recall, this was 0 point, then we had 11 zeros here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 8 millimeters. Actually, we should leave our units here too. Okay, so now how can we rewrite this as a number between 1 and 10 times a power of 10? Well, the only non-zero numbers in this number are this 8 at the end here. So let's do that. We have 8.8 is the only way we could write those as a number between 1 and 10. Times, now what would we have to multiply 8.8 by in order to get this long number here? Well, in a sense, what we can do is we can simply think of how far over that decimal place had to move. Right? If it starts at 8.8, so this is where we want the decimal place to end up when we write it in scientific notation, how many spots was that? Well, we can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12 spots that it had to move over. So when we multiply 8.8 times 10 to some power, we need to multiply it by a power of 10 that will move the decimal place 12 spots over here. Move the decimal point 12 spots over here to the left, starting here at 8.8. And the way we move the decimal point to the left to get really small numbers is to multiply by a negative exponent. And we're going to have to multiply by negative 12 because we need it to move over 12 spots. Right? We could also think of this as 8.8 times 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then the 1. So this is a scientific notation way of writing the radius of a proton. This that we started with is the standard notation way of writing it. Notice how the scientific notation way is much faster. Well, notice fundamentally the pattern that we see here we notice that the exponent tells us how many places the decimal place will move when we go from scientific to standard notation, or vice versa. Right. We can see here that here the decimal place had to move 12 places. Here the decimal place, how many places did it have to move when we start with the 3? 1, 2, 3, 4, 5, 6, 7, 8, in fact. That's what we got here. So we saw here it had to move 8 places. Now, the difference between these two examples is, in this first example, the decimal place had to move 8 places to take 3 times 10 to the 8 in scientific notation. To take that 3 in the scientific notation case to the standard notation, it had to move 8 places to the right. If we wanted to go from standard notation, the 300 million to the scientific notation, 3 times 10 to the 8, you would have to move 8 places to the left. Notice multiplying 3 times 10 to the positive 8 is going to get us a pretty big number. If we had instead multiplied by 3 times 10 to the negative 8, we would have gotten a small decimal. Right, now let's look at our second example. Here, to turn 8.8 into this 0.000000000000088, we'd have to move the decimal place 12 places to the left. To go from this big long decimal back to the scientific notation version, we'd have to move the decimal place 12 spaces to the right. Fundamentally, if we take a number like 8.8 and we multiply it times 10 to a negative exponent, we're going to end up with a small decimal. So there are two things to notice about scientific notation. The exponent tells us how many places to move it, but also tells us which direction, right? Multiplying by 10 to a positive exponent gives us a big number. Positive exponent, big number. But a negative exponent gives us instead a small decimal. I encourage you to think of it that way rather than thinking of moving to the right or the left, because the problem is in each of these examples we could move to the right or to the left depending on whether we're starting with scientific notation and moving to standard notation or starting with standard notation and moving to scientific notation. We can see the speed of light is a pretty big number. If we want to move from that big number in standard notation to the 3 that's present in scientific notation, we have to move the decimal place 8 spots to the left. But if we want to move from scientific notation, where we have just the 3 times 10 to the 8, to standard notation, where we have 300 million, we have to move that decimal place 8 places to the right. So if you try to memorize or think about whether a positive or negative exponent means moving to the right or to the left, you have to do it in the context of thinking, do I mean moving to the right or the left when I'm going from scientific notation to standard notation, or do I mean moving from the right to the left when I'm going from standard notation to scientific notation? It's easy to get confused or to lose track there. If you just keep the idea in your mind that scientific notation that involves a positive exponent means you're going to get a big number, and scientific notation that involves a negative exponent means you're going to get a small decimal that's less than 1, then that can help to clarify whichever way you're going. You should know what you should get. You know that if you start with standard notation with a really big number, you should end up with scientific notation that has a positive exponent. And if you start with standard notation that has a small decimal that's less than 1, then you should end up with scientific notation that has a negative exponent. And likewise going the other direction. If you have an expression in scientific notation with a positive exponent, you know that your answer should be a big number that's bigger than 1. And if you have a scientific notation expression that has a negative exponent, you know that what you should end up with is a decimal that's smaller than 1. Okay. So we'll go ahead and start a new page. Let's write down the formal definition of scientific notation. So that we have it. We've pretty much already stated it, but let's write it down. A number is written in scientific notation if it has the following form. A times 10 to the n, where n is an integer, and the number a is greater than or equal to 1 and less than 10. Any number can be written in scientific notation, although we only usually bother writing stuff in scientific notation if it's particularly big or particularly small. For example, writing the number 10 in scientific notation doesn't make a lot of sense because then you have to write 1 times 10 to the first power, which is a bit longer. But writing 100 million in scientific notation does make more sense because you get to get rid of a bunch of zeros. So I want to point out a few things before we move on, though. Notice an important part of this definition is that a has to be between 1 and 10. It can be equal to 1, but it can't be equal to 10. The idea is it can really only have one digit in the ones place and some stuff after the decimal place, but nothing else. So for example, if you recall, when we were looking at our radius of a proton, we got 8.8 times 10 to the negative 12. This is correctly written in scientific notation. Millimeters were our units, actually. Now, this could also be written, for example, as 88 times 10 to the negative 13, or 0.88 times 10 to the negative 11. These are all equal expressions. This is equal to this, and this is equal to this. But the problem is, these are not written in scientific notation. And why are they not written in scientific notation? Well, because you'll notice this is not between 1 and 10. This is not between 1 and 10. This is too big. It's equal to 10 or larger. And this is too small. The only way to write 8, to put a decimal somewhere in that, to make it between 1 and 10, is to choose 8.8. 8.8 is definitely between 1 and 10. So be careful when you're writing things in scientific notation to be sure that that first number, the thing that you're multiplying by 10 to some power, is truly between 1 and 10, or equal to 1. It can't be bigger than 10 or equal to 10, and it can't be smaller than 1. So you have to be sure that you put the decimal point in the right spot. Essentially, you're going to want one number to the left of your decimal point for that whatever goes in place of a there. If you always make sure that you have one number one and only one number to the left of the decimal point. If you make sure you do that, your number will always be in scientific notation. Okay, so let's go ahead and practice doing some examples. All right, to start out with, let's try to write this in scientific notation. Okay, how might we write it in scientific notation? Well, we need to start by thinking about where do we want the decimal point to end up eventually? Well, let's look. What are the numbers that we have that are non-zero? This 4 is non-zero. That's the first place where we have non-zero stuff right here. So we've got 407 as something that needs to be turned into a number that's not 0. So our A is going to have to come from this. So our A is going to have to be 407 with a decimal place somewhere. Well, we know we always want that decimal place to be right after the first number. This works because 4.07, this is in fact between, this is bigger than 1 and less than 10. So that's good. Now we need times 10 to some power. What power do we need here? Well, we can see this whole thing is a small decimal. So we know we're going to need a negative power. A negative exponent. Now, what size should that exponent be? Well, we need to ask ourselves, how many places do we need to move the decimal place? Well, we want it here after the 4. That's what we figured out over here. So how many places is that? 1, 2, 3, 4, 5, 6, 7 places. So it'd be 10 to the negative 7. So our final answer in scientific notation would be 4.07 times 10 to the negative 7. Let's try another example. What if we wanted to take 2.3 times 10 to the 7th power, and we wanted to write this in standard notation? In other words, we want to write it as a regular old number. Well, we're going to do the same thing we did here. We know that since this is positive, the exponent is positive, that tells us that the number we end up with, we should end up with a big number. When I say big, I mean a number greater than 1, something that's not a small decimal, right? Okay, so we need to figure out, if we start out with 2.3, to get a big number, the decimal would need to go to the right. And how many spaces should it go? It should go 7 spaces, because the exponent is equal to 7. Decimal should move 7 spaces in whatever direction we need to get a big number. So that means we're going to move to the right. So we go 1, 2, 3, 4, 5, 6, 7. That's where the decimal should end up. And then we need to fill in any holes there with zeros. I want to be sure that I do that carefully. One mistake people make is they fill in zeros without making sure they get exactly 1 in each spot. So we got 1 in each spot. And so what do I end up with then when I'm finished? I end up with 2, 3, and then 1, 2, 3, 4, 5, 6 zeros. 1, 2, 3, 4, 5, 6 zeros. And then I add in my commas where I need to. So here I get 23 million. Let's look at another example. Again, let's try writing something in scientific notation. Okay, now this is a pretty big number, so I know I'm going to write something in scientific notation that's likely to have a positive exponent. And so I need to figure out, where do I want my decimal point to be when I write the A part, the part that's between 1 and 10. Well, that needs to be all the parts of this that are not zeros. So I have this. Notice there is a 0 in the middle here. That's okay though. That 0 that's in the middle has other non-zero numbers on either side. Notice it has a 5 here, it has a 6 here. So this 0 in the middle here is just going to have to be a part of my A, because it's a part of the expression that has non-zero stuff in it. So I know that the A part, I have 3, 6, 0, 5. All of that's going to have to go in my A part. Where should the decimal point go in order to make sure that this number is between 1 and 10? Well, it has to go right after the 3, because remember, I'm only allowed to have one number. I need one and exactly one number to the left of that decimal point. So now I just need to ask myself, okay, how many spaces did I have to move that decimal point to get it there? Well, if I put my decimal place here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces, because this is where the decimal point is really when I have a number that doesn't have any numbers after decimal point. It always goes after the ones place. So that means that I need to multiply times 10 to the positive, because this is a great big number, so it's going to be positive. And how many spaces again? 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces is how many spaces the decimal place moved. So this would be times 10 to the 9th power. So 3.605 times 10 to the 9th power. Let's try one more example. I'm going to write in standard notation the following: 6.97 times 10 to the negative 8. Okay, so what do we know here? We know that our answer is going to have 6, 9, 7 in it somewhere, and it's either going to have a bunch of zeros before that or a bunch of zeros after that. Now, we can see that the exponent is negative. This tells us that in standard notation we should have a small decimal, in other words a decimal that's smaller than 1. And the 8 tells us we need to move the decimal point 8 places. Well, where is the decimal point we started? It was after the 6. That's where it started. So we need to move that decimal point 8 spots, and which direction do we need to move it? Well, if we moved it to the right, we'd end up with a big number, which is not what we want. Because this is a negative exponent, we know that we're going to have to move it to the left to get a small decimal. So we'll move it to the left 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. This is the new spot where the decimal point should end up. I can fill in zeros in all of these empty spots, and being very careful to put exactly 1 in each spot. So what I should end up with is 0 point, and then how many zeros do I have here? 1, 2, 3, 4, 5, 6, 7 zeros. 1, 2, 3, 4, 5, 6, 7 zeros. And then 6, 9, 7. So here we go. We have our answer in standard form, and I can double check that it makes sense in that this is a negative exponent and this is a small decimal, so I probably went in the right direction. And I can see here that I've got 7 zeros here, which makes sense given that the exponent was a negative 8 and I had this 6 in front of the decimal point too. So I had to move this decimal point 1 spot to get behind the 6, and then 7 more spots that had to be filled with zeros. Now we may also want to multiply or divide expressions that contain scientific notation, but notice that scientific notation is just like the exponent expressions that we've already looked at. Some number, for example, times a power. And we know how to simplify powers when we multiply them, when we divide them, and so forth. So we can do the same thing with standard notation that we've already done. So now that we've completed this lecture, we should be able to take really big or really small numbers, any number really, that's in standard notation, and we should be able to write it in scientific notation correctly. We should be able to take any number that's in scientific notation and write it in standard notation. And using what we already know about exponents, if we were given something written in scientific notation and we needed to multiply it with another number in scientific notation or divide or simplify expressions, we already know how to do that because scientific notation expressions are just like any other exponent expressions. They follow exactly the same rules because they contain exponents. So you should be all set now to complete any homework assignments on scientific notation.